So today we're going to be talking about chemical bonding. Now throughout the trimester, we've been learning about singular atoms, elements, and their structure, behaviors, and properties. In this chapter, we will be learning about the structure, behaviors, and properties when more than one element comes together. When two or more elements come together, they form chemical bonds. And chemical bonds is a mutual electrical attraction between the nucleus and valence electrons of a different atom that binds the atom together. And there are two types of chemical bonds we're going to learn today. The first type is ionic bonding. Ionic bonding is chemical bonding that results from the electrical attraction between cations and anions. We already learned previously that cations are positively charged ions and anions are negatively charged ions. And we know cations are positive because they're losing those electrons, and anions are negative because they're gaining those electrons. Now, an ionic bond is a bond between a metal and a nonmetal. And the metal becomes a cation, whereas the nonmetal becomes an anion, because in an ionic bond, which we learned last time, there's that transfer of electrons, the donation of electrons. The metal is becoming a positive charge ion, the cation, because it's losing the electrons, but it's transferring, it's donating the electrons to the nonmetal, because the nonmetal is becoming that anion, that negative charge, because there's a gain, so it's gaining those electrons. So again, there's that transfer of electrons going on in ionic bonding. Next one is covalent bonding. Covalent bonding is chemical bonding that results from sharing of electron pairs between two atoms. So now this time, there's going to be some electrons being shared. There's not any donations, not any transfers going on. And this bond happens between two nonmetals. And there's that share of electrons. So ionic is between a metal and nonmetal. Covalent between nonmetal and nonmetal. Ionic, we have that transfer of electrons, but covalent, we have the shares of electrons. So looking at our periodic table here, the one we just looked at before, from the 10 characteristic groups we have, we can determine how many elements are, we can determine what elements are metals and nonmetals. So our alkaline metals, alkaline earth metals, transition metals, and metals, all of these are going to be classified as metals. Our nonmetals, halogens, and noble gases are our nonmetals. And if you remember when we talked about metalloids during chapter 5, is metalloids act as both metals and nonmetals, so they're going to be classified as both. Now regarding our lanthanides and actinides for this chapter, we're just going to ignore those because we're not going to go into depth of what they look like when they're in compounds. So with that idea, let's go ahead and do some practice problems. We're going to determine what type of bond, ionic or covalent, is occurring in the following compounds. Again, ionic bond is a metal and nonmetal. Covalent bond is nonmetal, nonmetal. The first example we have is NaCl. Our first element in this compound is sodium. Sodium's here, and sodium is actually a metal. Our next element here is chlorine. Chlorine's over here. Chlorine is classified as a non-metal. So we have a metal and a non-metal. Metal and non-metal is our ionic bond. Problem number 2, we have CO2. Our first element here is carbon. It's not cobalt. Remember, cobalt is a lowercase o. This is a capital O, so it's two different elements. Carbon is classified as a non-metal. Next element we have is oxygen. Oxygen is also classified as a non-metal. Non-metal, non-metal is covalent bond. Now we have H2. Our first element here is hydrogen. Hydrogen is a non-metal. But our second element is also going to be hydrogen because H2 means it's HH. First element is H, second element is H. So still, hydrogen is our second element, also a non-metal. So non-metal, non-metal results to a covalent bond. Now we have Fe3O3. First element here is iron. Iron is a metal. Next one we have is oxygen. Oxygen's a non-metal. So we have a metal and a non-metal. Metal and non-metal is an ionic bond. Now I'll go ahead and do this example on your own. When you have your answer, press play. It's covalent bond. Now go ahead and figure out what bond this is. It's ionic bond. So now covalent bonds have two different classifying bonds now. Nonpolar covalent bonding, and that is a covalent bond in which the bonding electrons are shared equally by the bonding atoms. And for something to be nonpolar, their electronegativity difference has to be between 0 to 0.5, so anything less than 0.5. But we're never going to have a negative difference between the electronegativity. That's why I'm not putting less than 0.5, because we're not going to get anything less than 0. Our next type is our polar covalent bonding, and that is a covalent bond in which the bonded atoms have an unequal attraction for the shared electrons because their electronegativity difference is greater than 0.5. So nonpolar, we have that equal share. Polar, we don't have an equal share. So one atom is being favored more with the sharing versus another, where nonpolar, they have that equal share amongst each other. So to figuring out something is polar, nonpolar, you're going to be using this electronegativity chart. If you notice on all the areas where atomic masses would be, you would know, wait, that's not the atomic mass. Because those numbers are actually your electronegativity numbers. That is what you're going to do to find the difference. Remember, difference means subtracted. We're subtracting. We're going to be subtracting those electronegativity. So let's go ahead and do some practice problems. We're going to figure out if the following is going to create an ionic, polar, or nonpolar bond. First example we have is carbon and hydrogen. Carbon is over here, and carbon has an electronegativity of 2.55. Hydrogen is over here, and the electronegativity is 2.20, so we're going to take 2.55 minus 2.20. When we do that subtraction, that difference is 0.35. Now 0.35 is less than 0.5. Anything that we have less of is going to be indicating a nonpolar covalent bond. So that's your answer for problem number 1. Now we have oxygen and hydrogen. Oxygen here has an electronegativity number of 3.44. Hydrogen has an electronegativity of 2.20, so we're going to take 3.44 minus 2.20, and that equals 1.24. Now 1.24 is greater than 0.5. So anything that's going to be greater than 0.5 is going to reflect a polar covalent bond. And now we have NaCl. And sodium's here, chlorine's here. But this combination is not going to reflect a polar or nonpolar because it's not even going to create a covalent bond. It's actually going to create an ionic bond because sodium's the metal, chlorine's a nonmetal. So your answer of this one's actually ionic bond. So when in doubt, if you're ever given a metal for any problem involving bonding, your answer is always going to be ionic no matter what. So for these types, you don't even need to do any subtraction. Oh, I know there's a sodium there. Sodium's a metal. I already know. I'm not going to do subtraction. My answer is ionic. So go ahead and figure out what type of bond this is going to form. And it's ionic. Now go ahead and try this problem on your own. It's going to be polar. And then finally go ahead and do this one on your own. And this one's nonpolar. So now we're going to go into our final part about intermolecular forces. Now within bonds, they have forces called intermolecular forces. Intermolecular forces are forces of attraction between molecules. And there are 4 intermolecular forces we're going to talk about today. Our first type is ionic, which is ionic bonds. Again, like I just said before, regarding bonding or intermolecular forces, if you're given a metal in the problem, your answer is going to be automatically ionic. Next is hydrogen bonding. Now, it's pretty much when a hydrogen atom that are bonded to a highly electronegative atom attracted to an unpaired share of electrons of an electronegative atom in a nearby molecule. Essentially what this means, it's a force between a hydrogen and an oxygen, nitrogen, or fluorine. So whenever a hydrogen and an oxygen are forced together, that's hydrogen bonding. Hydrogen or nitrogen, that's hydrogen bonding. Or hydrogen and fluorine, that's also hydrogen bonding. Next one, we have dipole, and that's created by equal but opposite charges that are separated by a short distance. Essentially for this, polar bonds can have dipole. So anytime you have a polar bond, your force that's going to happen is dipole. And then we have our London dispersion force. We abbreviate that to LDF, so you can always just write LDF. You don't need to write the big, long London dispersion force name. And that's attractions resulting from constant motion of electrons and the creation of instantaneous dipoles. If it can create a nonpolar bond, it's going to have LDF. So with that idea, let's go ahead and do some practice problems. We're going to determine the intermolecular force, ionic, hydrogen bonding, dipole, or LDF, that is present in the following compounds. So whenever we do these, we want to first eliminate ionic and hydrogen bonding. If we know that our problem is not going to be ionic and is not going to be hydrogen bonding, that's when you can do your electronegativity differences. So number one for hydrogen and hydrogen. First, we're going to see if it's ionic. The only way it would be ionic is if you're given a metal. Well, number one, neither of these are metals, so we're going to move on to hydrogen bonding. Remember, hydrogen bonding is a hydrogen-nitrogen, hydrogen-oxygen, or hydrogen-fluorine. Yes, problem number one, we have hydrogen, but we do not have nitrogen, oxygen, or fluorine, so it cannot be hydrogen bonding. That is when we're going to do our electronegativity differences. Hydrogen's electronegativity number is 2.22. We also have another hydrogen with the same electronegativity number. That results into 0. And 0 is less than 0.5. We know previously that less than 0.5 is nonpolar. Whenever you have nonpolar results, your answer is going to be LDF. So moving on to problem 2, we have carbon and oxygen. First thing we're going to do is eliminate ionic. Is there any metal present on this one? No, there's no metal present, so it can't be ionic. Now moving on to hydrogen bonding. Well, there is no hydrogen in this problem, so it can't be hydrogen bonding. So now we're going to do our electronegativity differences. Carbon is 2.55, oxygen is 3.44, and we actually get negative 0.89. Whenever you get a negative number in your difference, you're just going to ignore the negative number. So really, we're only looking at this number as 0.89. 0.89 is greater than 0.5, which we know is polar. If we get an answer that reflects to polar data, it's going to be dipole. Problem number 3, we have hydrogen and oxygen. First thing we're going to do is eliminate ionic. There is no metal in problem number 3, so it cannot be ionic. So let's move on to hydrogen bonding. We do have a hydrogen. Now remember, it has to be hydrogen, nitrogen, hydrogen, oxygen, hydrogen, and fluorine. Well, this one, we do have an oxygen. Therefore, automatically, your answer is hydrogen bonding. Problem number 4, we're going to first eliminate ionic. In this problem, we are given a metal. Our metal is sodium. So since we're automatically given a metal, when in doubt, your answer is ionic. So with that idea, go ahead and do example number 5 on your own and press play when you have your answer. Answer is LDF. And then lastly, go ahead and do number 6 on your own. And our answer is hydrogen bonding. And that is it. Thanks, guys.